Hi, this is Rafiq. Welcome you to my class. Today we continue with the rotation operation again. I have chosen benzene molecule for you today, and I have also marked an axis here which is passing through the center of the molecule. We all know benzene is a planar molecule with the 6 carbon atoms and 6 hydrogen atoms. All those one in gray color are carbons and the white ones are hydrogens, and the axis is passing through the center of the molecule. And now you see a 60-degree rotation through this chosen axis. You see hydrogens and carbon atoms are shifting their position to the position of next carbon and hydrogen. So you get an indistinguishable image from the initial one. You see, if I have marked one of the hydrogen as with a star here, that starred hydrogen will shift its position here, and these two images are indistinguishable. So you get, when you rotate this molecule through 60-degree rotation, you get this image. These two images are indistinguishable, therefore you have a axis of rotation, a symmetry element axis of rotation, and a 60-degree rotation operation is possible in this molecule. And if you rotate it again, one more 60-degree, this starred hydrogen will reach this position, that is this image. So you have another 60-degree rotation possible. If you rotate it third time, you get this, fourth time this, fifth time this one, and sixth time you get the initial image, original one. So have a look at this. When you do 260-degree rotation, instead of, if you are doing a single 120-degree rotation like this, if you are doing a single 120-degree rotation through the same axis chosen here, you get this image, the third image. So 2 times 60-degree rotation is equal to a 120-degree rotation. That means this is a C6 rotation, this is another C6 rotation. So C6 2 times equal to a C3 rotation. That means why it is C3? 360 divided by 120 is equal to C3. So this is a single C3 rotation, that is equal to 2 times 60 or 60-degree rotation or C6 rotation. So C6 2 is equal to a C3 rotation. If you do a third time rotation, that is C6 3, this is C6 1, C6 2, C6 3, third time rotation, C6 third time, that is actually equal to a C2 rotation, because when you rotate this molecule through the same axis by an angle of 180 degree, what you get, this starred hydrogen will reach this position, that is this image, you see. So therefore this is a C2 rotation. You can get this image directly by rotating 180 degree instead of 360-degree rotation. So therefore you can say C2 is equal to C63 or C63 equal to C2, and this is the fourth 60-degree rotation. You are shifting the position of these atoms once more. So that is C64. That is again equal to C3 2 times. If you are doing one C3, you get this image, and second C3 you get this image. Therefore C3 2 equal to C64, and this is C65. When you rotate it this molecule once more, you get this image, that is C6 fifth time, C65, and that image you can get by rotating this molecule through the same axis clockwise. Clockwise rotation of 60 degree. You can take this starred hydrogen here, that is this image. So that can be indicated using a symbol called C6 inverse is equal to C65. C6 inverse is equal to C65, and this is the sixth rotation. C6 6. I haven't written C66 here. So C66 is equal to the initial image that we generally represented by capital letter E. So C6 6 times is equal to E. That is actually identity operation. So identity operation is the operation of not doing anything. If you are leaving this molecule as such without doing anything, that symmetry operation is called identity operation, and that is represented by the letter capital E. So C6 6 times is equal to a doing nothing operation, that is identity operation E. C6 6 times is equal to E. When we do not do anything, we leave the system unchanged and identical to the original system in all respects. So it is denoted by the symbol E. Though E may appear to be superfluous operation, it is mathematically very necessary to include in our symmetry operation. So E is very relevant in mathematical aspects. In every object, in every molecule, you have at least one symmetry element or one symmetry operation that is represented by the letter E. It is there in every molecule, that is doing nothing operation. Every molecule has a symmetry with its own image or on its own. That symmetry is represented by the letter E. That is doing nothing operation. You leave the molecule as such and it has a symmetry on its own. Again, we come to the benzene molecule. Let me take you to the website back. Let me mark another C2 axis, which is again perpendicular to the plane of the molecule, which we have already discussed. That is C6 is third time is equal to C2. I was actually looking for another C2 axis. Yeah, it's here. You see, I have chosen 3 C2 axes. They are all passing through 2 carbons and 2 hydrogens. If you rotate one of those, you see this is the new image. So you have a C2 like that. In the same way, you have another 3 C2. You can also take another 3 C2. They are all passing through the carbon center of the carbon bonds, which are facing opposite. You see that yes. Now you rotate that. This is another kind of C2. So you have 2 types of C2 axis which you can represent like this. One set of C2, they are all passing through carbon and 2 sets of carbon and hydrogens like this. And here you have another three sets of C2 which they are all passing through the center of carbon-carbon bond which are facing each other like this. You have two sets of C2 axis, and in benzene molecule you have a C6 axis, you have also a C3 axis, you also have a C2 axis, you have a C6 inverse axis, and you have a C3 2 or C6 4 axis. Let me take you to another example. Tetrachloroplatinate. Tetrachloroplatinate. It's again a planar molecule. It's always better to take you to the website. Tetrachloroplatinate. It's here. It's again a planar molecule. Yeah. You can have a C4 axis which can be represented like this, because on a 90-degree rotation you get a indistinguishable image when you rotate the molecule through this axis. So 360 by 90 equal to 4. So this is a C4. If you rotate it once more, it will come here to this position, that is actually equal to a 180-degree rotation. So C4 2 times is equal to a C2. And you can also have C2 axis like this. If you rotate, if you want a demonstration like this, this is actually molecule is rotated through this C2 axis, which is passing through the platinum and two fluorine atoms. Another C2 like this through this axis. So you have two C2 axis. You also have another two C2 axis which is passing through platinum like this. So you have two sets of C2 and a C4 here and a C2 also here and a C4 inverse also in the tetrachloroplatinate molecule. If you take an example of PCl5, trigonal bipyramidal molecule. Let me take you to the website. It will be definitely D3H. Phosphorus here. It is phosphorus pentafluoride, that doesn't matter. Yeah, you see the molecule, phosphorus pentafluoride. Here you can have a C3 axis which is passing through phosphorus and two axial chloride atoms. You can want a demonstration. Yeah, you see. And the C3 inverse also. C3 2 times is equal to C3 inverse. You can have C2. Let me show you C2. Like this, you have three C2s. See demonstration of one of those. Yeah, you see that it's beautiful. See this. Oh. Another C2 like that. Another C2 like that. You have three C2 and a C3 and C3 inverse. So that's about the rotation operation, and I hope from all these discussions you must understand what is symmetry operation, what is a symmetry element, and how to perform a symmetry operation, and proper axis of rotation and rotation operation,